Hello, everybody. Welcome back. Good to see you guys. Just a few of us, I guess, for the moment, but I'm sure the numbers will just start to go up as we get into class time. Hope you guys had a great weekend and are doing well. We will start in just a few seconds here for our Monday morning, November the 2nd, Intro to Logic meeting. Hey, Marissa, good to see you. Hi, Jamie. Jamie, I hope you got my email with the screenshot of the problem set. Hi, Ella. Good to see you. Okay, guys. Well, thanks again so much for being here, and let me just get us started. So what we're doing, and as you guys all know, is we're just working through this derivation content in the class. That's the only thing that's left to learn. All the other concepts, we've so far dealt with. Now our goal is to just become as good as we can at conducting proofs, proving things by means of the derivation system of sentential logic, SD. So as far as we've come to this point, we've learned a certain number of the basic inference rules, and the ones that we've learned are reiteration, conjunction elimination, conjunction introduction, disjunction introduction, conditional elimination, biconditional elimination. And there's still 3 more rules that we have to master. I'm going to teach you guys 2 of those remaining rules today. Oh, and yeah, we've done biconditional introduction too. So there's 3 rules left. There's negation introduction, negation elimination, and the disjunction elimination rule. So we're not going to get into disjunction elimination today, but we are going to cover the 2 negation rules. So for every one of the 5 logical connectives, there are 2 derivation rules. There's an introduction and an elimination rule. Like, for example, conjunction introduction is a rule that allows you to create a conjunction from 2 previous lines in the proof. Conjunction elimination is a rule that allows you to disassemble a conjunction on a previous line and remove one of the 2 conjuncts from it on a subsequent line. Well, there's also the connective called the negation sign. And just as there's 2 rules, one introduction, one elimination rule for conjunction, for conditional, for biconditional, there's also an introduction and an elimination rule for the negation. So that's what we're going to try and cover today, the 2 negation rules. So we're going to start off with what is called negation elimination. Don't forget, by the way, that the 3rd homework is due on Wednesday. That's not today, of course, but in 2 days from now, between now and then, you should be sending me your, your attached file, just containing your answers for the 3rd homework. And this morning, I was a little pressed for time before class, so I did not yet get to send around to the whole class the announcement with the office hours for today, the Zoom link, but I will do that right after class. So, as always, my office hours are Mondays and Wednesdays from 1:30 to 2:30, and the invitation's always wide open for anybody who wants to swing by and drop in on the Zoom if you want to ask any questions about anything. Okay, so just a little reminder about course dates. After Wednesday, when you do submit this current homework, then I'll distribute the 4th and the final homework, and then you'll have a couple of more weeks to work on that one in advance of the final. So after you turn in the 3rd homework, basically you have 1 more and then the final. So 2 more things following from the 3rd homework. Okay, so let us go over this. Negation elimination. As we've learned, in the justification column of the proof, when you do an inference, you have to write the symbolization for the rule. And with negation elimination, as you probably can imagine, the relevant symbol is this. It's tilde sign E. Okay, so negation elimination. Hey Leo, how's it going? Yeah, so this one here. I have some better markers in here. I just need to find the correct one. Okay, let's try that. Okay, so the negation elimination rule. So here we're just showing the schema for how it works. It's a rule that revolves around the subderivation structure. So, so far with subderivations, we've learned how to use that to do conditional introduction and biconditional introduction. But these negation rules also involve a subderivation. So when you start off doing negation elimination, you basically have to do this. You assume some statement. Suppose you assume not P, okay? And then within the subderivation here, as the scope line continues downward, suppose that inside the scope of the subderivation, you get two sentences that are opposites of each other, okay? So like say you have Q and then not Q, tilde Q. If a statement and the opposite of it can both be derived from this assumption, that means that we can then close the subderivation, and outside of this broken scope line, we write the opposite of this statement, in other words, P. So it's called negation elimination because in this rule, you assume a negated statement, and then through a series of inferences, you try to establish a contradiction is what it's called, okay? So a contradiction is a statement and its opposite. Like a contradiction would be me telling you that I am older than 30, and it is not the case that I am older than 30. Like those two sentences are logically inconsistent with each other, as we've learned earlier in the class. They cannot both be true because they're saying opposite things. Like if I told you that, I don't know, there are more people in America than Mexico, and also there are more people in Mexico than America, that's contradictory because one sentence claims something and the other sentence denies the same information. So the concept of negation elimination is based around an actual tactic of argument that has always been with us and is used every day. The idea behind it is you establish some thesis by, at least for the sake of argument, assuming the opposite of what you would like to prove. And then you try to show that if that assumption were to be held, that it would lead to something impossible. An unacceptable, impossible thing follows from this assumption. And therefore, by assuming the opposite and establishing this contradiction, we thus prove the contrary of what we sought to assume here. For example, okay, let me try to prove to you that the Earth is not flat, all right? In Latin, there's a name for this strategy of argument, and just so you know what the name is, it's sometimes also called Reductio ad absurdum. Hey, Peach. Good Peach. Good kitty, yeah. So reductio ad absurdum, which means in Latin to reduce to absurdity. So the way that a reductio style argument goes, as I was just mentioning, is you would like to prove some claim. So the first step of trying to prove that claim by means of reductio is you assume the opposite of what you want to prove, right? Then, on the basis of this contrary assumption, you try to show that something absurd or impossible results, namely a logical contradiction. So let me try to prove to you by means of reductio that the Earth is not flat. Forget for a moment the technical symbolism and just attend to what I have said about reductio. When you're trying to prove a claim by means of reductio, you have your claim you want to prove, but you assume to begin the opposite of that for the sake of argument. So if I would like to prove that the Earth is not flat, then the first step in reductio would be to assume for the sake of argument that what? I'm trying to prove it's not flat. So reductio says assume the opposite and then see where that goes. So I'm trying to show it's not flat. So then in terms of this methodology, the first step in my proof would be to assume what statement or what fact. Just a question for you here. Just let me know in the chat. Remember, the claim I'm telling you I want to prove is that it's not flat. So what's the negation of it's not flat? What is the reverse of not flat? That it is flat. Okay, good. So reductio ad absurdum. I want to prove it's not flat. So let us assume that it is. Now, if the Earth is flat, what's something that is implied by that? If that were true, what's something that that would mean is also true? In case the Earth is flat, assume, just suppose. If it were, tell me something that would be implied by that that's kind of a little strange. Just asking you from a level of common sense. I mean, in case, you know, if the Earth was flat, can you tell me something that that would imply? Something that would imply, which seems to be contradicted by other facts that we're all aware of. So just please tell me some random or not random thing that would imply. Well, yeah, okay, good. That's one thing to mention, Lily. If the Earth was flat, so let's assume it is, well, that implies that photos taken of the Earth from space show a disk. But, as we all know by having looked at these photos, what do they look like in reality? The actual case is that when we see photos of Earth from space, what is shown in such photos? Lily, since you made the suggestion, maybe you've got something here. That it appears round. Okay, good. So follow the logic. I want to prove it's not flat. Okay, so like a lawyer, let's assume the contrary to see where that would lead. On the assumption that it is in fact flat, that means that photos taken of the Earth from space will show a flat disk. But that is not what the photos show when we look at them from space. So we can thus conclude that it is not flat, right? The assumption that it's flat led to a contradiction. It implies that there's a fact which is contradicted by something that we know is true. So in fact, therefore, it's a sphere. And we could have said more. If it's flat, that means that objects approaching the edge should fall straight off the edge because there's no curvature on a flat disk. But of course, objects do not, in fact, fall off the flat edge of the Earth. So on the assumption that it's flat, something would happen, but that does not actually happen. And so it's not, in fact, flat. That's how reductio ad absurdum works. Or in another case, I'm the detective, and I'm trying to say in court why I have evidence that so-and-so Smith is guilty, right? Smith pleads not guilty, but I'm a person who's trying to give evidence to the jury that he is. So I say to the jury, well, the defendant claims he's not guilty. So let's suppose that he's not guilty. If he's not guilty, that means that he didn't commit this crime, which also should mean that his fingerprints should not be on the murder weapon and his blood should not be splattered around on the crime scene, right? So if he didn't do it, then we shouldn't find these items on the crime scene, but we did find them. So therefore, he must have committed the crime, right? Assuming that he didn't leads us to this contradiction that there shouldn't be signs of his commission of the crime, but yet there are. So thus we must conclude that he did it. That's how reductio ad absurdum works. I'm just trying to give you the bigger logical backstory to this very sketchy looking set of symbols that you see on a board. The way that the rule works, yet again, to just recap and summarize, is you want to prove something, like in this case, you want to prove P. So we assume initially that not P. And then if we can determine a series of, through a series of inferences, two propositions which are contrary to each other, then we can close the subderivation right then once we get the contradiction, and we see that it spits out the reverse of the negation assumption. We call it negation elimination because the initial assumption is going to be negation something. And the conclusion reached on the basis of the rule is going to be the unnegated version of the statement. Okay? So let me show you like one example of how this kind of works. Yeah, so let's try this one here. I'm looking at a problem that is written in the book on page, well, it's not a problem, it's sort of a practice thing, but it's on page 161 for you to refer to later if you want. Okay, so here's just a way of looking at an application of the rule. Okay, so say we have this problem here. It says just derive n. And it provides us these three assumptions. Okay, so the first one is that if not n, then s. The second one is if s, then c. And the third one is if C, then N. Okay, so all you know is you need to derive N. Oh, let me see here the questions. Yes, you do. Sorry, Evelyn. You write the word assumption, ASS. I was simply taking my time and putting it on last, but good. Okay, yeah, so the fourth step is going to be our first inference after we've got these three assumptions given. Our goal is to get N. Now, I'll just tell you as a sort of freebie that the first move of this proof is going to be negation elimination. When you do negation elimination, you create a subderivation like so. You indent over, and you have this second vertical scope line, and you assume the opposite of what is to be proven. And so in this case, we want to prove N. So what's the opposite of that to be assumed at the start here? It'll just take a moment. We'll work through it, but we're learning this rule. We want to get N. Negation elimination says that when you want to prove some statement, you can assume the opposite. So if we want to get this, we must start by assuming its opposite. And good, Jamie, that is tilde N. So here's how the justification looks. You slide over to the right and you write assumption, letter A, for negation elimination. Okay, now we're started off. Now, keep in mind what's to be looking for now. We've assumed not N for negation elimination. Now the whole game is try to get a contradiction in here somehow. Okay, try to get two sentences where they're opposites because one of them has a tilde in front of it and the other one doesn't. Okay, they're the same except one has a tilde prefixed to the left side. So we're not yet 100% sure where the contradiction will come from, but we're going to try to find it. Knowing now that we have not N available from our assumption, that should open up an idea about what the next step could be. So who can suggest what the next step could be on level line 5 here? I've taken you as far as line 5. Help me take the next step. Not N was step 4. So what do you think I can do next? Given the fact that, you know, all of our inference rules and the 4 things available in the proof to this point. What would be your next inference? Tell me the sentence and what the rule is. Okay, so Lily, you're telling me S on line 5, coming from conditional elimination of 1 and 4. Correct. S, conditional elimination, 1, 4. Are we all clear about where S has come from? Conditional elimination. So once not N was added to the proof, you would go back and look at the other steps. And you would try to see, is there any place where this information also appears above? You would then see that your eye is going to notice line 1, where not N is the antecedent. And if you just remember the rule of conditional elimination, having these two things available allows you to eliminate line 1 and give you S. But we're not done until we get this contradiction, okay? So what's the next step then, maybe, on line 6? Line 6, give me an idea about that next inference. There's kind of going to be a little pattern following from what we just did in line 5. So take a look at line 5, look at the above lines. Okay, Brenda, for line 4, why is the A next to tilde E? Because this signifies assumption. When we start a subderivation, we always write the letter A off to the right because we are making a new assumption. The A stands for assumption. Subderivations always open with an assumption. So they always say A and then the symbol for the rule. Okay, so assumption for negation elimination. That is why we have tilde N. So hopefully this can answer your question, Brenda. A is there because what it means is assumption, negation elimination. When you open a subderivation, when you create the second vertical line like this, subderivation rules have to start with letter A and then the name of the rule. Okay, so Arlene, you say that I should have C here now. And that's also from conditional elimination of line 2 and 5. Good. Okay, notice. Line 2 is a conditional. It says if S, then C. Line 5 says S. So those two steps combined, just as with 1 and 4, 2 and 5 combined gives us the consequent, which is C. All right. But we can't stop. We can't stop until we get that contradiction inside the scope of the subderivation. And to this point, we still don't have it. So what do you say on line 7? Line 7 is next. There's one specific thing that should occur to you about line 7 now. So just tell me what it should be. Line 7 of the proof. What's the next step? The next inference to make. You gotta let me know. Okay, good. Nathaniel, you're saying, yeah, almost Brenna, except it's number 6 combined with 3. Good. Okay, so n here. N, what's the basis of writing n? Well, that's also conditional elimination, and it's the combination of 3 and 6. Okay, because 3 says that if C, then n. 6 says C. Those two things allow you to eliminate the conditional and just write out the consequent. Okay, we're very close now to finishing this proof. Not to worry, good Brandon. So we want to finish this proof, but we can't do it until we have a contradiction in here. Now, notice that within the scope of the subderivation, line 7 says letter n. What's the opposite of n? And is there a way to get that in the scope of the subderivation? Good, Lily. Tilde n is the opposite, the reverse of this. If we have those things in a pair, then we can close this down and then we'll get what we want. But how can we get tilde n on line 8? It's easy. There's one inference to do it. It might not occur to you immediately because we're not yet in the habit of doing this, but yeah, reiteration. Correct, Lily. So we reiterate from line 4. That places tilde n here on line 8. Notice that now we have a pair of contradictory statements. Line 7 says n, line 8 says not n. But this is impossible. And therefore, we can discharge this assumption of tilde n and get its opposite, which is that letter, the letter n. That comes from negation, elimination, and then we're going to cite the numbers between where the first assumption is and where the scope line ends. So that's 4 through 8, 4-8. Okay, and this is the proof that we were looking for in this particular case. So just know that anytime you are going to use the rule of negation elimination, you'll open the assumption with some negation sentence, and you'll try to then follow the inferences until somehow you get a pair of sentences that are opposites. Now, in this case, the pair of opposites, one of them was the assumption reiterated, and the other one was the letter n. Sometimes the contradictory pair will not be one of the sentences that was assumed, but some other stuff that was already in the proof from elsewhere. So depending on the particular example, the contradictory pair could involve the statement which was assumed initially, or in other cases, it could simply be a contradictory pair of statements obtained from other parts of the derivation. Okay, so this is how negation elimination works. And I want to quickly then also demonstrate for you guys how negation introduction works. The good thing about these two rules, negation elimination, negation introduction, is that it's kind of like two rules for the price of one. Understanding the one is really nothing different than understanding the other. The only difference between them is what kind of sentence is assumed at the beginning of the subderivation. So now let's go into this. We're talking now about the rule which is called negation introduction. And as you might guess, it's the symbol for it is tilde I. Okay, so in the case of negation introduction, you will start the rule by making an assumption in a subderivation. In this case, suppose you assume P. And then suppose that subsequent to that, within the subderivation, you get these two sentences, Q and not Q. In other words, a pair of contradictory statements. At that time, you can close the subderivation and then break the scope line, and at the tail of it at the bottom, you write the negation of your original assumption. So negation elimination and negation introduction are really not different. The only difference is that in negation introduction, the conclusion, the output is going to be to add a tilde to the sentence assumed at the beginning. In negation elimination, the output at the end will be to strip off a tilde from what was assumed to start. But the procedure, once you make the assumption, is exactly the same. Find a contradiction, and then close the subderivation. So let me give you an elementary example of this type of problem here. I'll leave the rule up on the board for the moment so that you can consider it in conjunction with the problem here to the right. Okay, so suppose that I say derive this. Derive tilde h. And you are given these two premises to work on. First of all, h, then f, if h, then f. Second, it is not the case that f, tilde f, the negation of f. Now you want to derive tilde h. Last problem that I just explained on the board, I kind of helped you by doing the first step. But this time I want you to take those training wheels off a little bit and tell me how you think I should start this problem on line 3. Keep in mind, I'm trying to find negation h, and you are learning negation introduction. So that should suggest to you the following procedure. What is the first inference, perhaps? Okay, good, Tanya. H will be assumed for negation, not elimination, though. Let's get the name correct before I write it up there. What rule will be used? Yes, negation introduction, correct, because in this case, the output in the end will be to have a negation statement. Okay, good. So we assume H for the sake of negation introduction. Okay, now, before I continue, let me ask a more conceptual question here. What is the goal now? Having assumed that H, what is going to allow us to eventually close this subderivation if we can get to what? What becomes the sort of micro goal right now within just the subderivation, taking leave for a moment of the larger goal of obtaining tilde h? We'll get to tilde h, but we won't get there until we first find what within the subderivation. Inside of the subderivation, we need to have what elements? We need to have, I'm just asking about the mechanics of this rule so that does not get lost on you. Nathaniel, I see you writing the letter F. Yes, true. But yeah, in broader terms, we're looking for a contradiction, right? We're looking for two sentences where one is the opposite of the other one. And you're right, Nathaniel, to be specific about it, that's going to involve these letters here. Anyway then, fourth step. Tell me what should be written on line 4 and what is the justification for that. Anybody can let me know how to go on now into line 4. There's not too many steps in this problem, just a few more. But on line 4, what should it be? Okay, good, Arlene. F, on the basis of conditional elimination, 1, 3. There's F. All right. Well, we're not done yet, but we're making progress because getting F is like half of a contradiction that we can create now. Well, what's next, you say, on line 5, in order to follow the rule structure of negation introduction? Correct, Arlene. Let's write tilde F. Why? Well, it comes from line 2, in which, as you can see, already says tilde F. We just need that to appear inside of the scope down here. So tilde F is reiteration of line 2. So then, what is the result here on line 6? How do we finish this one out? Because we are at the end. Good, Arlene. It's tilde H, and that comes from the Negation Introduction rule, lines 3 through 5. Okay, so where did this tilde H come from? It came from the fact that on line 5, we got the second member of this contradiction pair. Once you have the two things that contradict, you are then able to close the subderivation that you started off by assuming H. And the outcome of that is that it basically spits out the reverse of what was plugged in as the assumption. So the negation rules have an output that's always the opposite statement of the assumption. When it is negation introduction, this opposite statement that results is going to be opposite by adding a tilde to the original. And when it is negation elimination, this opposite statement that results is going to be something that eliminates a tilde from the initial assumption. Okay, so that's just the only real distinction, if anything, between the two rules, negation elimination and negation introduction. So now that we've gone over the rules, I want to take a moment to try and work on some more of the practice problems in the book, and I'll pull up, our dual platform so that we can all look at the shared screen and have a clear view. So let me put the Zoom chat here, and as usual, as you guys know, just click on it. I'll be right there. I'll continue to let this YouTube video roll so that people later can come back to it and watch the demonstration and discussion of problems if they want. Okay, so here is the Zoom, and now I'm opening it up. Okay, guys, here we go. Hopefully everyone can clearly see me. I'm going to share my screen. Okay. And pulling the chat up over here to the corner. Now, yeah, so anyway, you see here, by the way, can anyone in our Zoom chat just quickly confirm everything's working well? You hear me, see the video, see the screen? Okay, good, thank you. This is just a reproduction in the text of the rules that we're currently now learning, negation introduction, negation elimination right there. On page 161, you would see the problems just shown. This one here on the board in 6 steps is the problem listed here on page 161, just to illustrate how negation introduction works. And the previous one, that was slightly longer, that we did before that, is also shown below here. Okay, so I want to take us to problem set 5.1.2. And let's try and do some of these little problems here. Like, for example, let's try to do this one, problem C. Okay. Okay, so what we're looking at then is problem 5.1.2, part 1, and it's problem C. Okay. Good. So let's try this one down here. It's this one. I'm trying not to display all the different steps so that we have a little bit of a challenge. Here you got to derive B. And your only premise, your only assumption is that if not B, then B. Okay, so you've got to get B. What to do? Please tell me, what inference may we start off with? And again, consider the new rules and how they may be used in deriving the letter B. So we want B. Okay, good, Tanya. Negation elimination. So let's assume what on line 2 then? If it is negation elimination, we must assume what statement? In order to, at the end, get B, we must start by assuming what statement? You're right, it is negation elimination. So Frida and Tanya, it's correct. We will assume B. No, sorry. We're not assuming B. That's not correct. It's negation elimination, not introduction. So tell me again, this is incorrect. What is to be assumed on line 2? Tilde B, yes. Assume for negation elimination. Because, right, if it was B that was assumed, that would be for negation introduction, and the result then at the bottom would be tilde B, but this is the goal. So if this is the goal, you assume the reverse. The reverse of this is that. Okay, now having assumed tilde B, just look at the problem and tell me what's possible to do in the third line. You have 2 steps. There's a very, very limited number of possibilities here. And if you know all of our rules, then the correct rule should just be obvious right now. What's the rule and the inference on line 3? Okay, Frida, it's B from conditional elimination 1 and 2. Do we understand this third step that Frida just talked about? Everybody? Look at line 1. It's tilde B, arrow B. That's a conditional. Conditional elimination is when you get the antecedent on another line, those 2 things combined output the consequent. And that's what we have. Conditional elimination 1 and 2 gives us B. So we continue going further, keeping in mind that since we started this subderivation, we'll eventually have to get a contradiction. Okay, well, we can get this contradiction quickly in short order, but you need to tell me how to get there in the next step. So what is the next step as we are working within the subderivation that started on line 2? Okay, Lily, yes. Tilde B from reiteration of 2. But Frida, I'm a little confused about what you have written. Tilde B is what we want here. And that's just reiteration from line 2. So there's no question yet of negation. I mean, negation introduction doesn't work that way either. Negation introduction is a rule that you cite in only 2 possible cases. Number 1, when you're starting a subderivation, but we're already in the midst of one. Another case would be where you're citing it as a justification for closing the subderivation. But negation introduction is not a part of this proof at all. It's negation elimination, you see. So that's out of place. Tilde B is easier to get. So it would be overthinking it to think of negation introduction and stuff. It's just tilde B is line 2. So it just gets reiterated. Okay, so then on line 5, what's the result? I see that, good, Frida, and 10, you're already telling me that it's B, which is based on negation elimination 2 through 4, correct. And there we go, in 5 steps, we've arrived at the needed result. Here you can see, let me pull up some of the answer key stuff. Hold on. Yeah, right here. So just if you see right here, this proof is the same one on the board. You've got to derive not B. The only assumption provided is that if B, then not B. We assume B for negation introduction. Sorry, which one am I looking at? I'm looking at C. Okay, this is B that I was now displaying. So this is actually a very similar proof, but for the opposite result. 1 second, guys. Sorry about that. I need to just pull up the other one. I got to just scroll to the right section. Yeah, okay. Here we go, thanks. So in order to derive B from the one conditional assumption of if not B, then B, we assume its opposite for negation elimination. With that opposite assumption in place, we can now eliminate the conditional in line 1, giving us B. Notice that the opposite of B is tilde B, which can be reiterated from line 2, and then in the 5th step, we've gotten to the solution. I guess we can also try the other one. So let's just do that to kind of make this even more clear. Oh yeah, so let's do this one really fast. This is in section 5.1.2 part 2b. Okay, this problem. Very similar proof, but just to be a little more deliberate and clear and patient with you guys, derive not b. And all you have here to work with is if b, then not b. So let's see if we can follow along and get this problem solved. We want not b. This is our only assumption. If we want not b, tilde b, then what could be assumed on line 2? Line 2 assumption. Tell me about it. To start the proof off, the outcome in the end is going to be tilde b. But to get there, we got to start off with this assumption and think about how these negation rules work. One rule is negation introduction. One rule is negation elimination. Negation introduction introduces a tilde as the outcome, the final product. Negation elimination strips the tilde off as the outcome and the final product of the proof. Well, what we want is something with a tilde. So, good. You're saying assume no, Frida. It can't be negation elimination, which is assumed, because we want a negation. We're not wanting to eliminate a negation. We want to create a negation. So let's try again. B is assumed for negation introduction. Okay, so line 3. Now B has been placed in the proof. Follow the logical steps forward then. Now that we have B, what is the subsequent step that follows afterwards on line 3? B is there. So all at once, tell me, please, what is the next step? Because I have no idea and I won't tell you. You have to tell me. So every time you want to derive tilde, it is introduction. Yeah, it's true. If you want to derive a statement with a tilde, you have to use introduction of negation. Elimination means you're taking tildes away. Introduction means you're adding tildes. If what you need is a tilde statement, you need to introduce negation, yes. But good, Tanya. So not B from conditional elimination 1 and 2. Okay. So then what's next? Yes, good, Loveth. That's correct. But we got to know where to go next on line 4. It's like the last proof. So this one, I hope, isn't the worst difficult problem. Yeah, B, reiteration from 2. So then, having obtained a contradiction in the scope of the assumption, which we started with B, what is the procedure to do now on line 5? Yes, good, Tanya. To write not B from negation introduction 2 through 4. And that would be the proof of this problem. Okay, perfect. So we're just going to keep doing endless practice problems. That's all this is nowadays in our class. And that's good. So let me take us back to 5.1.2 problem C. Oh, wait. No, I got that one. I mean to say D. Okay, this one here. Let's try that out. Alrighty, so the problem says derive that if A, then not B. And we have 2 assumptions. First of all, if A, then if B, then C. and the second assumption that not C. So this one will take a few more steps, and it'll take a little more thought, but we're all here to help each other, so let's just try. First of all, my question is this, and you should always ask this question when you see a problem. What's the main connective of the sentence that I've been told to derive? And what is it? What is the main connective of the derived sentence that is your goal? Correct, it is the conditional. So when you need a conditional, what rule suggests itself? Anytime you need to establish a conditional, you should have the thought of what inference rule. Conditional introduction, very good, Lily. Tell me the procedure one more time to give us a little refresher. If we would like conditional introduction to build this sentence, we must assume what to start that subderivation? When conditional introduction is utilized, the first step of doing it is to assume what? I know conditional introduction is from last week, but we will never forget it. You will remember it throughout your entire life. So it's the antecedent that is assumed, yes. That's the right idea. So what is the antecedent here, please? Just tell me then in more specific terms. What shall be assumed on line 3 in the purposes of proving this proof? Correct, Frida, it's A. So A is assumed for conditional introduction. Now, what will be our goal to ultimately reach somehow inside of this subderivation? The consequent. Whenever we get there, then we'll be good to go. But we got to take it step by step. And it's not going to happen all at once. So just thinking one step at a time, what do you believe can happen on line 4? Every time a new line is entered into the proof, consider how it may be available and how it may be then used to make further inferences. Because, you know, we did not have A until we got line 3. Now that we have it, more stuff can be done, but you must see what it is. So what is the next step that you do see, given the fact that A is now one of the lines in the proof? You look at what's previous to the new line in combination with the new line, and you ask yourself, can these pieces be applied to each other by any of the inference rules? So we've added A on line 3. And I repeat my question, what is line 4? Okay, good, Lily. B, then C. And that is not conditional introduction, though. Let's say it clearly before I write it on the board. Yeah, conditional elimination, and it is lines 1 and 3. Okay, good. Okay, so there is B, then C. Okay. So now, the next step, sorry, oops, I caught it, I'm sorry, step 5. The next step is one that might be a little bit not immediately obvious to some of you guys, but that's fine. But I'll just give you a hint. It's going to involve a sub-derivation. You guys ever heard of those Russian dolls where there's like a doll within a doll? Well, this is like that. We're in a subderivation, but we need to create a second one inside of the first one. So what do you believe could be this sub-derivation that I'm talking about? To make an assumption of what statement? Because remember, ultimately, this thing won't close down until we get to not B. So if not B is like the little mini goal right now inside of this subderivation, ask yourself, how can I make a step next that will help me get to not B, tilde B? The rule that we're learning today is coming into play now. So I'm giving you big hints. What can be assumed perhaps on line 5? It's a little logical leap, but just don't be afraid. You're not the first person to do logic at all. In fact, you're way down in the ancestry. This is thousands and thousands of years old. You're learning things that our ancient ancestors talked about in ancient Greece, and it will still be the topic of instruction in another 100, 200, 300 years. It's pure reason, it's pure logic. But yeah, anyway, I'm asking you a question, and I need you to tell me the answer. What is another step to now make on line 5? Because we're trying to get not B inside the scope of this subderivation. No, you cannot write not B then not C. There's no inference rule that allows this, Nathaniel. But I'm trying to tell you, we have to make an assumption on line 5. It involves our new rules. We're trying to get to not B. Okay, Frida, what rule are you using if that's what we should add on line 5? Tell me the justification, not merely the sentence, because you have to say both of those things. Yes, correct. Absolutely, Frida. Very good. B is assumed now for the sake of negation introduction. Because if we can introduce a tilde to this, then the output of it will be not B, and then we can close this and we'll be done. Okay, so on line 6, now we have this little subderivation. It's a negation introduction assumption. So what has to be inside the scope of this little subderivation is a contradiction, a pair of contradictory statements. And we'll get there, but we just got to do this one step at a time. So tell me on line 6, now that we've added line 5, go back and look again and tell me, does that open up any new options, given that there has been this addition of line 5 to the problem? Okay, good, Lily. C results from conditional elimination 4-5. Okay? There is the letter C inside of this little baby subderivation. Keep all of these moving parts in your mind at once. Inside of this, the little sub-goal is to get our contradictory pair. And right, Frida and Lily, we can reiterate line 2 into line 7, which provides us with a contradiction of C and then not C. So since we have this contradiction, what's the outcome on line 8 of closing the subderivation? Line 8 is when we will close this guy up. And when we close it, what is the final line of that subderivation? Okay, good, love it. It's not B. And let's just know the justification that I'll add to the right. Not B comes here. But over on to the right, what is the rule that I'll cite? Yes, it is negation introduction involving lines 5 through 7. Yeah, 5 through 7. Okay, good. One last step. What is the last step? Yeah, 5 through 7, because the rule is whenever you're giving the numbers and you're closing a subderivation, the numbers span from where the first line starts the assumption to where this vertical line breaks and you end it. And that starts with 5 and it goes through 7. Okay, but anyways, on line 9 is my question. What is the final step? As we should know, the final step of every proof just says the derived statement. So that much you should know. But what is the rule? A then not B. And it is from Conditional Introduction 3 dash, not comma, but dash 8. Yes. That's Conditional Introduction 3-8. And there you have this proof of, what did I say, problem 5.1.2, part D. Or problem D. So let's just quickly see here. This is without the justification column included. You just see the rules there. Conditional introduction, Tanya, yes. Conditional introduction is the rule that started on line 3 and extends all the way through to line 8. This scope line doesn't terminate until we reach the desired consequent. This consequent was obtained midway through the subderivation by starting another subderivation with negation introduction as its basis. Okay, so yes, that's correct, Tanya. Let me pull up the answer key on this one. And we'll just try and see how that looks really fast. Not this particular section, but here. Right, and so, sorry, let me scroll this up a bit. You see here, everybody, this is the exact proof that we've just done as shown in the answer key. Two assumptions. Start by assuming the antecedent of the desired conditional, right? So like, sometimes I feel like a student learning logic, another example of conditional introduction, sure, Tanya, let's see what is the next problem I was thinking of doing and see if it involves that. Look at H, G. So if you want to do another conditional introduction problem, I'm just trying to find one that's like suitable to the difficulty level. Many of these back here didn't use it yet because they're kind of like lower difficulty problems. Let me go to the other answer key and see what's available there. If I can't find one quickly, then I'll just create one. Okay, so, all right, yeah, let's try this one then really fast. We'll do this problem here, which is in section 5.3, part 1, just because you request another conditional introduction example, which is no problem at all. So yeah, let's do that. Okay, so what I'm looking at right now is this problem shown here, which says derive that if A, then both A and B. Okay. And one assumption is provided, which is just if A, then B. Okay. Okay, so what's the goal? It's A arrow parentheses A and B. So what's the main connective of the sentence that you're told to derive? I'll start with that question for you. What's the main connective of our goal sentence currently? Okay, good. It's the arrow. It's the conditional sign. Sometimes in the book, you know, it's the horseshoe, but we've been mostly using the arrow. So, I mean, like for one more quick statement of why I prefer the arrow somewhat is because it shows directionality. It shows that to the right is the consequent. The horseshoe almost looks like it's pointing back at the antecedent. So this is, I think, a little bit more specific. And at UCLA, where I studied logic initially, they prefer the arrow. Anyways, okay. We need to then build a conditional. And when you need to create a conditional, what rule should you think of first? To build a conditional, to build any statement which has that as its main connective, we need to think of the rule conditional introduction. Okay, great, Evelyn. So we want conditional introduction to build this sentence for us. To do that, what's the algorithm, the procedure? When you're doing conditional introduction and you want some sentence, you start by assuming one part of it. So tell me on line 2 then, based on what your knowledge is, what should be this assumption for conditional introduction? We're all on the same page that this sentence you need is a conditional. I think we're on the same page that it's conditional introduction that will get us there. So just, you know, you're supposed to know, how do you start conditional introduction? Yeah, you assume the antecedent, which is what? In this example, it's A. Okay. Assume for conditional introduction. Conditional introduction, you start a subderivation. That means a new little indented line, and you assume the left part that's on the left of the arrow. That's how conditional introduction works. You assume the thing to the left of the arrow, and then you need to obtain eventually the stuff that's on the right. So what is our goal now inside of this subderivation? What's the goal? What's the goal to get to before we can close the subderivation? If we eventually get what result in the subderivation, then we can close it. No, not B. Sorry, Evelyn and Brenna. It's not merely B, because that's not the consequent of the needed statement at the top. What is the consequent? It's A and B, okay? Just understand that the full information that is on the right of the arrow, whatever it is, it could be a full formula, it could be a single sentence, but whatever it is, that stuff, all of that on the right of the arrow is what you need to get inside of the subderivation that you start with conditional introduction, okay? So, I mean, don't overthink it. You need a conditional, you assume the left, and then you need to prove the right. The right part needs to then appear somewhere inside of this subderivation. So we need A and B. We're not there yet, but we can get there, but it's going to take a couple of steps. So anybody tell me, what do you think I could do on line 3? Given the available lines of the derivation and our familiar inference rules. The third step, there's only really one way to go. What do you say? And loveth, no, A arrow B is not it either. It's A and B, as you can see. So anyway, line 3. Go ahead. You need A and B, right? So how to do it? You have to make an inference. See, logic, sometimes the student is like, where do I go next? The thing is, you're the only one that can do it. Like, no one else can do it for you. You have to make the inference. If you're waiting for like some external aid or some external source of information to like give you the answer, it's got to come from up inside of you. You've got to tell me how to make the inference because you're doing this deduction. Okay, Frida, B comes from, remember how conditional elimination works? You have to cite 2 lines. So you're almost there, but you have to say 2 numbers. So it's 1 and 2, good. All right, so we've got B. What's the goal again? Don't forget it. What's the goal inside of the subderivation? A and B, right. So keep your eye on the prize. How do we get A and B? We can get there now in one step. But you need to remember the rules. Okay, Lily, A and B is from Conjunction Introduction 2 and 3. Okay, where did line 4 come from? Lily, you see it. It comes from combining these 2 things, adding them together. A plus B is A and B. That's conjunction introduction. Adding together line 2 and 3 together gives us this, the conjunction of the 2 statements. Okay, so A was our initial antecedent assumption for conditional introduction. Through some steps, we've gotten to the required consequent. So now, what's the procedure and how do we close the subderivation? Okay, so Frida, A arrow, A and B, good. And it is from conditional introduction, and it's 2 through 4. 2 comma 4 makes it sound like there's only just the 2 lines referred to, but it's inclusive of all the intervening steps, including 3, the 2 dash 4. And there you have the proof. See it here in on the shared screen. Okay, so in reply to the question here from above, Tanya, another example of conditional introduction. Here it is. This is a conditional. We got it by conditional introduction. Conditional introduction says that if you want an arrow sentence, you assume the left side of it. Then you take however many steps it takes to get to the whole right side of it, which we did. Whenever you get to that right side element, that's when this gets closed, and outside of the broken line, you write the whole conditional, where this is the left side of the arrow, and the bottom line below is the right side. That's how conditional introduction works. Okay, good. So let me just do another problem real quick with you guys while we're all here. I want to try 5.1.2 problem B or C. Let me see here. Oh, not this one, actually. Sorry. Okay, 5.1.2, letter B, letter D. Okay, let's maybe try this one here. problem D that you see listed on the bottom of this little part of the screen. Okay, so what it says is derive H and not I. This one's a little bit kind of a little tricky, but it's actually deceptively simple. Okay, it's really not that tough, this one. If in the book they cite lines 2 through 5, will that change if our answer is right or wrong? 2 through 5, sorry Frida, which question are we referring to now? Did I make the wrong citation in my own problem just now? Let me go back up and see what you've mentioned. So you're telling me about problem yeah, so it was in section 5.3, was it not? I just don't remember the number of the problem anymore, so can you please refer me to the problem so that I can quickly just go back and answer your question? I don't remember what it was. Which problem was it? What, like, derive A arrow A and B? It doesn't say 2 through 5, so I need to find the problem. In the book, they cite lines 2 through 5, derive A, then A and B. Yeah, let me find the problem set where that problem is so that I can like go back to the solutions manual. Well, you're saying in the book, oh, okay. If you're saying in the book, where in the book? What page? Okay. And okay, sorry. So you're talking about on page 169. This is the stuff from the textbook. No, Frida. But the thing is, it's not correct. So look. Are we talking about this problem right here? Frida, is this the one? The one that's in 5 steps? Derive. No, it's not this one. Anybody can help me with this if you can find it. I want to give you a conclusive answer to your question, but I need to be able to find the problem that we're discussing. You say it's okay, but it's, as a logician, it bothers me. I need to know if there's an error or not. Sometimes the book contains typographical errors. When it does, then that needs to be corrected. Um, so what it said was, A, then A and B. Derive that. Does anybody remember what the assumption was that it provided for you? Did it say A arrow something, or what did it say? What was the first assumption? I'm looking at the A then B. Okay. So you need A arrow A and B. 2, assume A for conditional introduction. 3, eliminate this conditional, giving us B. 4, let's see, combine these two things, A and B. That is conjunction introduction 2 and 3. On line 5, it's A arrow, A and B, from conditional introduction 2 through 4. No, it does not say 2 through 5, and it doesn't say it in the book either. So it would not be correct to say 2 through 5. It would not. The required proof is of this form. When you cite in the justification column the last step that closes a subderivation, you're never to cite the current line, because it's only above lines that can ever be cited in any justification for any inference. So no, you may not cite the current line in any attempt to provide a justification in the justification column. Okay? I'm trying to see if it was one of the earlier practice problems. But yeah, it's just simply not the case that it said 2 through 5. So anyways, we're going to have to start this at the beginning next time, because I think that there's not sufficient space of time to like go through a full additional proof. But since I'm using so much of the time to try and get the correct part of the textbook for your question, I don't want to let it go just yet. I want to continue to try and search through the notes for the relevant problem that we were just doing. And I'll just see it if I scroll through every single problem, I suppose. Well, then it's getting into other completely different stuff. Let's see, is this the section that was mentioned? Well, yeah. Sorry, Frida, but it would be good when we're going through a question of that kind to have the clear citation of where or what you're referring to. You know, I don't want you to be confused about the way that the rules are cited when you close a subderivation. And so your statement that it says that in the book just bugs me, because it can't say that in the book, and I need to be able to like determine in the text where it seemed like it said that. But because I'm bouncing around from different examples, I don't think to myself, problem 158. Okay, sorry, on page 158, let me go back to that. So page 158. It looks like it has a citation like that, but it's a different problem. So at the top of this page, this problem, maybe Yeah. So in this case, we cite lines 2 through 5, but that's because we're on line 6. And line 5 was some available lines from above. The subderivation in this case extends from 2 through 5 before it is closed. So anyways then, yeah, to your question, no, you would not cite the final line in the subderivation. What I'm going to do basically to make sure that this is perfectly clean and clear is I'm going to go back and find the problem when I have additional time and leisure outside of class. I'll start the next class by going over the problem again. But it really was kind of an elementary problem. This is the solution to it. And yeah, you have to cite lines 2 through 4. The subderivation doesn't continue on to line 5. So it discontinues right there. All right, guys. Well, I'm going to let you go for now. Make sure to do your homework. Make sure that you turn it into me before class time on Wednesday. And if anybody has any questions, like for office hours or anything else, please let me know, and I'll be there today from 1:30 to 2:30. I'll send a link for that right after class. Okay, guys, thanks again. I'm going to have to go back. I'll watch the replay of the video, and then when I watch the replay, I'll find it again. So thanks, everybody, and have a good one. Thank you.